Okay, for people joining this live stream, we are looking at biological sequences and their implementation in Wolfram language, heading for the upcoming version 12.2. All right, so let's start off with this overview. So we've looked at some of this stuff, and have you been? I'm trying to remember where we had been at so far.
I think John has implemented many, if not all, of the suggestions from the last time. We met with some of the emerald folks for some of the secondary structures, and John has some initial implementations of the function overloading the string processing that you had suggested. I think that's
excellent. Okay.
Is it correct, John? That's a good summary.
I think that's right. Yes.
Okay, so let's just look through these functions to begin with. Okay, so we got BioSequence, BiosequenceQ. I hate these Q functions, but I guess we have to have it. Okay, so if I put an N in there, it will happily. What is it doing? Okay. What the heck? What was this about?
I think that's something just with the prototype build, but that should be the last time that you see it.
Okay, fine. But all right. Okay. Anyway, so this was a sequence, and somewhere in it has an N. And if I now say, so now let's say I want to make proteins out of this. How do I do that?
Say BioSequence translate.
What's the difference between convert and translate?
If you have, say, translate, you have more options about what translation tables you can use, and also you don't have to type the word peptide.
Okay, so if I just say this is the default eukaryotic, whatever they are, creature.
That's right.
But I mean, we already know it's a eukaryote from the fact that it has T's in it, right? Okay, now what just happened there?
So now it's given sort of all of the translations to the peptide sequences available from the sequence above. Expanding out into...
Oh, I see. It expanded, by default, it expanded the N into all the possibilities.
That's right.
Okay, so if I were to put another N.
Last week.
What's that?
That's what we said last week should happen.
Okay, so if I put another N there, why do I only get 4? Why don't I get 16?
Let's see here. So that happens to be at the third base, and the third base is often degenerate. They often will, many codons will map to the same sequence. So by chance, you've gotten ones that happen to map to the same.
Okay, I'm convinced. Okay. So wait a minute. So these are different. That dot means, what does that dot mean?
Dots are typically coded for the stop character.
Okay. All right. So what can I do with these things now? Can I, now that I've got these peptide sequences, what can I now do?
Let's see here. You can open each of them up. You can get things like molecular weights. You could do sequence alignment with them.
There's some kind of, okay, how do I get the molecular weight of all of these? What's the function to get the molecular weight?
Slot of molecular weight mapped over.
Nope.
No.
How do I get the molecular weight?
It should be molecule mass. I'm sorry, I was muted.
Sorry, yeah.
And why is it called molecule mass rather than molecular weight?
Oh, I know. That's a long history about this. This I know. We had endless discussions in the unit framework about this.
What is this? What is the right term?
Molecular made.
God, we still don't have that bug fixed with the selection and the prototype build. Does anybody know what's happened to that? Okay, what the heck is that plus dot?
That's probably we don't know the weight of the start codon.
Yeah, that should just be truncated. That's a bug.
Okay. Always good that I can find these in less than a minute. I'm not sure I managed to do it in this case. Okay, so now random instance of that biosequence. Okay, string match Q, circular DNA of this, beautiful. Okay, so now you're saying string reverse just works on these.
That's right.
And you're sure this is what we want, because I'm sure this will give some internal discussion.
I think so. We definitely don't want a biosequence string. Which ones are we supporting? I mean, if I do string repeat, will that work?
Not yet. The goal is just to work my way through kind of all of them on the string page. This is what just happens to be implemented as of this meeting.
I mean, there are many of them.
Not that many. I mean, string pad left. I don't know. Pluralize, we hardly need.
We don't need that one.
Things like edit distance, are we supporting that natively? Yeah, we do have those kinds of things, right?
We have string alignment. When we have the various string distances, I'll make sure that edit distance also works.
Okay.
So has it been discussed whether these functions, which also operate on lists of strings, would work on lists of biosequences? Because that cannot be done with up values.
I would not go there, honestly, because I think even the current behavior on lists is inconsistent.
I think that's a future issue. I take your point, and it's probably in a perfect world it would work correctly for that, but let's not worry about that right now.
Right. I just bring it up. That's something that the kernel folk often bring up when arguing against up value type things.
Right.
Okay. Okay. So we've got. Okay. So what is this? These are translation tables. Okay. Biosequence types: amino acid, circular DNA, etc. Let's see. Last time we ran into a bunch of biology questions which we couldn't answer. What were those questions? Can you remind me?
I think there was a question about, let's see here.
The question is about gluing things together, gluing sequences together.
Yes, that's the major one, yeah.
Okay, so explain that question.
So there is a compound biosequence, and kind of the question is kind of what's the standard, what was the standard interpretation of that?
Okay, but what does it mean, compound? Do we have that right now, a compound biosequence?
So yeah, if you go to the detailed section, and then new functions, biosequence, and then scroll down a bit.
Steve on our live stream is suggesting that iconography should look like the Mr. DNA from original Jurassic Park. I don't know what is it. What does that look like? Was it cool? Let me look. Images. Oh boy. Well, amusing, but I don't think it quite makes it. But highly amusing.
Could replace it with a wolf.
Yeah, right. Okay. In any case, the compound biosequence.
Yeah, they're still further down a bit. Let's see here. Yeah, we're still in the various forms of single ones. Keep going. Here we go. Sort of towards the end there.
Okay, hold on. Biosequence of BRCA1. I'm a little bit confused by this. How do I get, if I say, let me pick a different gene, because I want to pick a slightly, who knows, a simple gene. Let's see. I think hemoglobin gene. Isn't that fairly simple?
And I think there's some, you can ignore those error messages, those that more prototype stuff.
Okay, all right. So I've got this thing now, and now let's say I want to take this and I want to know. Well, let's just do this thing, molecular mass. Just so I'm just trying to understand what I'm getting here. So this would be okay. And now if I take this and I say string reverse a %10, then okay, that's cool. By the way, do we want in these summaries, do we want to give the beginning and end, blah, 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 dot, 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 end, like 2/3 at the beginning, 1/3 at the end? Anybody got a biology opinion about that?
Isabel might know.
I don't think that it would be much different from this. I don't think that it matters because especially for long sequences, it doesn't really matter whether you can see the beginning, end, middle, whatever.
But wait a minute. What I'm asking is, aren't the two ends more important than what's in the middle for lots of kinds of purposes? Or am I confused?
It could be for specific types of DNA, but I wouldn't say that's a general truth.
Okay.
Hey, Brad, what does Emerald do about this?
Yeah, we would show the beginning and the end just for that exact reason you have there. When I reverse it or reverse complement it, it's nice to just see that it matches up with what I expect.
That's a good point for kind of visual confirmation, yeah.
All right. Let's do 2/3, 1/3. 2/3 of the characters at the beginning, dot, 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 1/3 for the end. Do you get what I'm saying? John, you understand what I'm saying?
I understand, yes.
Okay. And I don't quite understand why you're not listing sequence. I mean, to me, it's an above the fold story what the sequence length is here. And it will be good to indicate that. It seems to me above the fold.
That's a great idea. And that'll particularly help with the 0 length sequences. Yeah.
Right, which otherwise will be utterly obscure.
The other possibility would be in gray over the dot, 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 how many?
Yes, I agree. Although I think you probably want to
don't want to count the first 10 yourself.
Yeah, right, exactly. I would just put paren in gray, how many there are. Length, length colon, whatever it is. Okay, but let's look. Where did you have these mixed things?
Build it up. You already went too far.
Oh, where? Oh, here. This thing here. Okay. Okay. What is none? I don't understand any of this.
Yeah, none is a convenience for when we don't have a standard alphabet that applies, and you just would like to put something in quickly.
Okay. The suggestion from Steve on the live stream is actually a little bit more contentful, which is could we use some color to indicate something interesting about the sequence in the icon here?
That's an interesting idea.
So make the active symbol or the icon dependent on the concrete sequence.
That's right, which we do in many other places.
Correct.
We just haven't done it here.
Correct.
If we can think of something interesting to do with it, I think that would be terrific.
Also, we typically don't do it if it gets too big, like a 500 meg interpolating function. We do not.
Indeed, we just punt to something generic. Okay, but let's go back down here. Okay, so what is this creature? This is a peptide sort of with a DNA, but you get those two things in actual chemistry and you put them in a test tube and they just hang out together, right? What do they do? It's a chemistry question.
The emerald people probably can most comment because my understanding is they deal with this situation a lot.
Can you say what a peptide meets DNA? What happens? Somebody, chemistry person, or
I don't know about peptides so much. Ribosomes obviously are peptides, and they do interact with RNA to make more proteins. But what comes to mind for me is microRNAs binding with single-stranded DNA to turn it off, for example.
Sure.
Or other transfer
But
RNA.
that's a binding, but that's not, look, what
well,
this
they're in a
looks
test
like,
tube. That's what you asked for.
Yeah, I understand that. Right. So what you're answering is exactly what I was afraid of, right? Which is, this makes it seem like you've got one sequence followed by another sequence followed by another sequence, but you're talking about binding, which is not that. That's
I think John has a future section for how to deal with this, with the binding.
Okay, but what does this mean? Does somebody know what this means? Because I think this is meaningless. Unless proved otherwise, I think this is meaningless. This is not an object that exists in the physical world, is it?
No, I feel like it's the same like a molecule. You have a molecule with 3 not yet bound together objects.
Okay, so
and
this
later
is
you
something...
bound either with hydrogen or with some explicit glue.
Okay, so do the Emerald folk have a comment on this? Anybody?
In our syntax, this would mean that the 3 pieces are conjugated together in some way. We don't currently have a way to specify that. That's something we talked about in the future. So it would be kind of implicit if there's DNA next to RNA. There's, physically there's something in the middle that makes the interaction happen, but they are physically bound together in the way that we represent it like that.
Would that be a linear sequence, or would be some kind of binding one strand to the other?
It would be linear.
Okay, end to end. Okay.
Yeah, the binding between strands with the hydrogen bonds and stuff is done through our secondary structure specification, through the bonds.
Okay. Okay. But
I feel like, to be consistent with our decisions already done on molecule, we must assume they're not yet bound together.
Right. So this is a biosequence. This is just a cluster of biosequence molecules, basically, that have unknown binding characteristics. A fair statement? These are free floating in a test tube. But this means, and again, I'm being perhaps very naive, but stoichiometrically, this means there's the same amount of this, this, and this. Is that true?
I don't think we make any statements about amounts here. Like with again, the parallel to molecule. If you have a molecule with 2 elements inside, we don't claim one of them is more frequent than the other.
No, but if you have NaCl and you've got just the Na and the Cl there, it's not Na2Cl7.
Correct.
Right. Even though you might not represent that as standard binding, right? It's still just stoichiometrically, it's some known ratio of those things.
Well, for molecule, it's exactly 1-to-1 for the NaCl example. It's not Na2Cl2 the way we.
Well, I understand that.
I don't like this interpretation, honestly.
Okay, all right.
Because I feel like we consider single things on the microscopic level. We don't make any statement about macroscopic concentrations.
Right.
Yeah, but I don't think you can say. It's like I have a list of numbers, 3, 7, 12. I've only got 1, 3, 1, 7, and 1, 12 there. I'm not saying there's any number of okay, this is a case. I don't know any case where we would think of a list of things and imagine that they're, it's some kind of generalized set where you're saying that it's these things in any concentrations. It seems wrong to me.
No, I don't think so. I'm arguing exactly the opposite. Because it's not macroscopic, the meaning of concentration makes no sense at this level.
Oh, I see what you're saying. Okay, so you're saying I've got this. Well, but look, okay, you're right that if I'm making an NaCl crystal and I don't know where the edges of the crystal are, saying it's an equal amount of Na and Cl doesn't really make any sense. If the crystal is small enough, the boundary is going to be a significant part of the story. Is that kind of what you're saying?
No, our molecule is literally just one single molecule. We could argue if in a radiation field or not, but there's nobody else around.
Yeah, I understand. But some things, okay, look, let's take, you say, xenon and, neon, okay? 1 atom of xenon, 1 atom of neon, Okay, what is it? What is the thing that you have? If we say molecule of xenon neon, what does it mean?
In infinite vacuum, under the condition of some background field that stabilizes the thing, there is somewhere one atom of this and somewhere one atom of this.
Okay, what would we say if we said we have a mole of, helium xenon?
That's an excellent question, and we had long discussions about this, and we have a Wolfram Alpha version of this, but we don't have yet a Wolfram language version of this.
Okay, but the answer is that in that case it's going to matter, right? Whether there's equal numbers, equal amounts.
Absolutely.
Okay. I think this is a mess, right? And I think that you're basically going to be, thrown into the question of, are these bound? Are they not bound? If they're bound, are they end to end? Are they somehow, binding to some, other part of the thing? I think this is a big mess. And I think this question about relative amounts is also a big mess. And how important is it? How important is it to support this? Who cares about supporting this? Why is this important?
Go ahead, Michael.
I think we heard from Trevor as well as from Emerald that this is a very common situation.
Can somebody from Emerald comment on that?
So we definitely need the way to stick things together. You mentioned, you're talking about amounts. We have sort of a separate way to deal with that. We have the notion of a state where you specify amounts of individual things. But even without the amounts, we want to be able to look at a set of things and ask what possible reactions, like what is the reactivity of this collection of things together. And the actual amounts you end up with depends on the concentrations.
I understand, but this is completely not that. This is a biosequence, right? To say that there's a collection of chemicals and then you do things with them, like you ask about reactions between them, that's a fine thing, but that's just a list of chemicals and you're asking about questions about reactions. This here says it's a biosequence that consists of a bunch of biosequences. Now, I did hear, I think Trevor in his lab does things with this, and maybe there's specific but I mean, this is not the story of. Go ahead.
Maybe let's take its simplest example. We want definitely to represent a double-stranded DNA. So yes. We need at least 2 strands of DNA that we put in one biosequence and then add hydrogen-hydrogen bonds.
Yes, but look, in this case, you've got end-to-end. If this means anything, it means there are 3 things this could mean. Okay, thing number 1: random molecules floating around in a test tube together. Okay. Thing number 2: end-to-end connections. 2 single-stranded pieces of DNA, glued together end to end. Thing number 3: 2 double single-stranded DNA things that are actually zipped together.
I strongly advocate number 1 because the only consistent interpretation with molecule.
Okay, but now, then how do I get from number 1 to number 3? How do I say zip them together?
John, did you not have a section further down? So John, I think you're muted.
Oh yeah, that's all the way down in the considerations for after 12.2. So.
Where should I look here? Oh, that's lovely.
Let's see here.
That's lovely.
Ah, great.
So I mean, we can just generate these, right? Given an RNA, we can generate this picture at decent speed. Is that a true statement?
Not yet.
Okay. And how? I mean, if we use like, I don't know, somebody's like Muhammad's, protein structure technology, is it worth us trying to put some protein structure computation in?
I would say in principle, yes, but let's first clear out the basics.
Okay. We should talk to Mohammed about that.
Yeah, he would have a lot of good opinions about the representation problem.
Well, he has actual technology for, that seems to be sort of leading the world at this point.
Indeed.
So we should talk to him about that.
But here you see how two RNAs are glued together.
Where do I see that? In here?
In the first one in the examples.
Oh my God.
And the generic bond we can discuss. We had already long discussion what kind of hydrogen bonds we need.
So this thing, okay? This is surely not the right way to do this. I mean, in other words, this is a generalized bond in some sense, right? A bond connects two atoms. This is connecting two, I mean, an atom is a point in the Euclidean sense.
No. I think you misunderstand. This is the C from number 1 with the A or with the G from number 2. It's not a quadruple bond between 4 things. It's index notation.
Oh my gosh.
It's referring to the bases, not to atoms within the molecular.
Right.
No, I understand that. But what happens if it's zipped? If the whole thing is zippered up, and most of the DNA is double-stranded, and it's got little pieces where it's, where at the end, it's got this giant piece of DNA, and it's mostly zippered together, but the zipper is open at one end. Does that? I mean, that obviously happens biologically, but I don't know whether does it. It doesn't stay in that state. It just unzips or it zips up. Is that right? Do you understand the scenario I'm talking about?
Yes, but I do not know if it's thermodynamically stable or not.
I thought it needed, a some enzyme-like thing. Can somebody comment?
That's right.
I would guess once there is a hydrogen bond, it should be reasonably stable.
Well, once the DNA is formed, but I'm asking the question. Look, I'm trying to understand, what is the structure? What types of molecules hang out there? Are there things where it is mostly double-stranded, but the double strand has come apart and it's single-stranded for a while? Is that a thing that happens, or is that not something we have to worry about for some reason? Can somebody comment on that? Does anybody know that?
That does happen with topoisomerase. That opens up the double strands so that one of the strands can be transcribed to RNA.
Okay. So this representation will be a total mess in that case.
We could use span or something in case they're long.
Fair point. So long as the syntax supports it, but that's something we're going to need.
Yeah, probably multiple spans.
There's a bit of an example above that where there's the text, the protein feature example right above there. There's kind of an example of a potential sequence notation.
Where is this now? Protein.
Right above there. Right at the end of kind of the RNA examples. It may be convenient to have a span form to capture a large number of lengths. Okay. And then you say that it's a bond sequence of some kind instead of just particular discrete bonds.
Does that have the right precedence? That whole puppy? Oh, it does. Wowee. Okay, cool. So that means that span. No, that's not consistent with what you just were feeding me. Okay, well, anyway, this is for the future. But
no, there were additional list brackets because here we have only one strand which is self-bonded.
Oh, gosh. Okay. All right. So basically, and what you don't have the capability to do is to annotate in sequence, so to speak. This is externally annotated.
Oh, that's the first. That's the first example there. Is giving some annotating some exons and coding sequences.
This thing here. Which
No, the one above that, the very first one, is doing some annotation.
No, but I know. But the point that I'm making is it is externally annotated. That is, the string is the raw string. Then you're saying there's annotation to the string. It's not. I'm just commenting on the design of the thing, right? It's probably correct.
I see.
But again, it's pretty similar to molecule. We don't serialize the molecule and have the bonds, atom, bond, atom, bond. We have first atoms and then the bonds. Or meshes, we first have the coordinates and then the primitives formed out of them.
Yeah, okay. Fair enough. Okay, so this is the sequence, and then this is the I mean, I don't understand why we've got lowercase exons and things like this.
That was derived from an existing standard, but that will change.
Okay. Okay, but so what is this? Okay, should we be looking at this? Let's concentrate on the 12.1 stuff. What else should we be looking at?
What's that?
Okay, what are the questions? What are the outstanding questions here?
So one major change from the last time was we got rid of the whole number of functions. We got rid of counting functions and inverse things, and we've really consolidated them. And,
I know, I can see that, and that's good. Okay, so let's understand here. Let's go back up to the top. Okay, so transcribe means this is 2RNA generically, is that right?
Right.
Okay, and translate is 2 peptides generically. Is that right?
That's right.
And we can translate either from RNA or from DNA to peptides. Is that right?
That's right.
Okay, what are the things that BioSequence Modify can do?
BioSequence Modify can currently jump to start codons. It can trim.
What does it mean jump to?
Codons.
What does it mean jump to? What does it mean jump to? Does it mean drop things that aren't?
That's right. It'll
okay,
drop,
so drop to
up
start
to the
codon. Okay, fine. Okay, what does flattened common subsequences do?
So if you have a compound sequence and then there's a DNA and another DNA, it will combine them. So it'll flatten them together.
Look, this compound thing is a mess, right? That's doing yet a different thing. What's that doing? Is that aligning from the beginning to decide how to compound them together? Do you understand my question? If you say flattened common sequences, is it the case that you line up the 2 DNAs?
No. They're still in sequence, but they become now one unnested one.
Right.
I see. So you're imagining that they form a sequence. So you've got a bunch of fragments.
Exactly.
Okay. Now I'm beginning to buy this a little bit more. So the case that seems to make sense to me is you've got a bunch of DNA fragments that you got from some algorithm, and then you've got a biosequence of a bunch of DNA fragments, and then you simply say, I want to put these all together.
That's
and
right.
I don't quite know why string join doesn't do that.
Would probably be done.
Yeah. Question of
Okay,
what
but
string
but
join
you don't
should
necessarily
do.
have biosequence on the outside. I mean, if you have string join, look, if you have a string join whose arguments are a bunch of biosequences, it should presumably join the sequences. If you have a string join that is a list of biosequences, unfortunately, that's implementationally difficult, but conceptually that should work. And as a hack, basically, for right now, if you say string join of biosequence of the list, that should just work. Does that make sense?
Yep, that's perfect if they're all DNA.
I understand. If they're not all DNA, we have no freaking idea what to do.
Right.
We should generate an error message. Unless somebody can tell me the chemistry of what should happen.
I think we should only do it for equal ones.
Yeah, and circular DNA. Good luck. What are you going to do? I mean, it's amusing, but I don't see what you do. Okay. Well, this all looks cool. Let's see, we have the folks from Emerald should comment on whether, I mean, if there's anything that they would like to see here, they should make sure it's known, because this is our opportunity. Okay, well, I look forward to being able to actually run this in your lab. And type in, I'm sure there's some function that you guys have where I can just give it some sequence here and I can say, go make me a vial of this and mail it to me.
Yes, we do. Not looking forward to translating our own system to this, though. But so far, I think from what we've seen last time and now, it supports pretty much all the stuff we can do now, at least.
Good. Well, hopefully it won't be too hard. I
Now it's your chance, Kanda, to push your things on us. Then you have less work to do.
That's true.
Okay. Well, let's see. What else should we do in this review? Sequence type, sequence string. What is chemical pattern list? Why is it? Oh, pattern list. Yeah, okay. If I say chemical list, let me try that. Will I get the obvious thing then?
What is
By the way,
the
don't forget to get get autocompletes set up for this BioSequence case. Right? Well, the obvious list would be the list of chemicals, right? If there is a list of chemicals. I don't know what it does in the case. Go ahead.
Yeah, that's kind of the question. What should I do then?
Well, maybe it should give an error message.
That makes sense.
I mean, I don't think we want to give the. I mean, a lot of the time it will be very definite, right? So this should certainly work, right?
Yeah, that makes sense. Can do.
Okay, this. Why is it called molecular mass here, but molecular weight in other places in the system?
I thought we had mostly phased out the weight, don't we?
Okay, all right, fine. So if I say something like caffeine, I don't even know what that means. Relative molecular mass. Well, at least it says molecular mass.
There have been a lot of discussion the last 10, 20 years in various international bodies that this weight was never a good idea to use.
Correct, because it doesn't have units.
I think that's what makes it so wonderful.
Wait a minute. Wait. This relative molecular mass is the unit-free thing, whereas molecular mass has atomic mass units. Is that correct?
When you ask for molecular weight, you usually mean the unitless version. Is the
correct?
Which is what you're now calling relative molecular mass.
That is the property name. Yeah.
Okay. So, but which is what everybody else would call molecular weight.
Correct.
Or
okay.
Did. It's phased out.
Yeah, well, phased by who? I mean, it's like I'm always
the
very
International Union of Applied in Pure Chemistry.
Yeah, I understand.
I mean,
I'm always suspicious.
I feel like, sorry.
No. I was going to make various silly comments about these international bodies that ratify different kinds of things and what that really happens inside those objects. But anyway,
right. I mean, at the end of the day, usage dictates meaning.
Exactly. What is this thing? Is it an interval? What is that?
Yeah, that's right. It has imprecise terms in it, so it calculates.
I understand that point. I'm trying to understand what it actually is. So if I say %16 divided by 7, for example, it'll just work. Great. Okay. You know, that font is very weird. and I think we could probably do something better than that. At least we can get, and this is a detailed thing for a different group of people. Okay.
Is it not the same font as the rest? Or
It is. I know it is, but it has weird
okay.
spacing.
So you want another one?
I think so.
Okay, I can discuss with Jose.
Yeah, I think so. It's not obvious to me, but it seems so. Because look, the point is that's not code, and it kind of looks like code. You see what I'm saying? It's like something which we have.
I see what you mean.
It confuses me. I'm thinking.
I see what you mean.
Yeah. Okay.
So I feel like we are not quite sure yet from what you are saying. So are you fine with the nested one, or do you don't want any nested one right now?
No, I'm now okay with the nested one, given that if you're nesting identical objects, identical sequence molecules, then I think I know what it means. It's end-to-end connection. What do you mean by nested one?
This is what I didn't think it would be.
Oh, listen, but you guys just told me that we can do a string join on it, and then it joins end to end.
Yes, but this doesn't mean before the string join they're already joined.
Well, but it means that you were to think of them as lining themselves up like that, rather than free floating in the test tube, where they could be in a different order.
But the question whether we want to allow whether we have a need for disconnected biosequence structures. Right? So like you can have a molecule that is just it's like a graph and it follows the rules of graph. You can have a disconnected jumble of atoms because it's just a microscopic model.
They like the precise molecular mass would be different because of binding energy.
Oh my God! What a can of worms.
So I mean, so with a molecule, you can have a disconnected structure, and it's useful.
Right, and you're going to tell me the distance.
Would it be useful for a biosequence?
Because if we do assume it is bound, then we need some more information. What exactly is the glue?
Oh, absolutely. Because what you're telling me, and I hadn't even internalized this point, is those little clusters of atoms, depending on how far apart they are, the aggregated thing will have different molecular weight because of different binding energy. Right? You pull these ionic thingies apart, they will have, less binding energy.
Yep.
I mean, it's usually lower than the precision with which you measure them.
Yeah, but even in principle, what a can of worms. Because we're going to end up with the same thing with nuclei one day.
Well, this is some 4 times 10 to the minus 10 approximately.
What is?
The relative change for many things, a couple of times 10 to the minus 10.
Explain that number. I mean, because that's like a meter compared to the size of the atom.
No, that's kind of mc squared, kind of the typical binding energy.
I see. Is electron volt type energy. Is that right? Yeah.
Which is today at the edge of what can be measured. So it's no longer fiction.
Right. Okay. So,
I mean, one other thing that we did discuss that we didn't write down is we could maybe have a very special head that glue off, and then you put your glue inside, like a certain exotic molecule.
But where is it? I mean, in other words, it's either gluing those sequences together end to end, or it's floating glue along with other stuff.
Right, but kind of this glue would mean it's not floating because it's not a biosequence.
Okay, let me show my complete lack of knowledge of biology. When you talk about things like phosphorylation and things like that, and these things, that's a modification to the sequence, isn't it? What happens? It's other molecules binding to pieces of the DNA or something. I'm very naive here. Can somebody help me out?
Phosphorylation on proteins is adding phosphate groups to things like serine residues that have a hydroxyl. So you're modifying one or more of the residues. Of the protein
so how do we
sequence.
represent when we have a protein sequence and we have some phosphorylation of that protein sequence? How do we represent that in BioSequence?
Yeah, that's with the below proposal, where we then say, along these particular terms, there's this particular link, which corresponds to this particular modification.
But what you're saying is that's this annotation. Is that right? That's how you would indicate things like that.
That's right.
Yeah, because they don't have a large enough alphabet to cover phosphorylation, methylation, farnesylation, or all other kinds of post-translational modifications that can occur.
And okay, another showing my utter ignorance, but these RNAi things, what are these? These little, what are they? Do they relate to this? What are they? Do you know what I'm talking about? They were all the
isocene, like in transfer RNA?
Well, RNAi is interfering RNAs.
Yes. How do those work? Isn't that some binding of one?
They bind, I think, with messenger RNA and interfere with its translation. Translation to protein.
Right, but don't they bind onto the messenger RNA? I mean, aren't they like maybe I'm confused about how it works.
I believe that's what happens.
So it's kind of like a generalization of things like this phosphorylation modification.
Yes, and it would happen. The actual binding would be over a number of bases.
Yes, I know that was so. What I'm hearing from you is this post-translation modification is a modified biosequence that has had, things, attached, on. Or
Yep.
in the case of the RNA, I don't think it's post-translation. It's it's actually pre-translation, right?
Yes, it would be. It would be. And the other things would be covalent methylation of DNA residues, or phosphorylation, as you had said, on protein residues. Those are all covalent binding events. And we would have to annotate, where it occurs in the given sequence, because the alphabet doesn't have special letters for that.
Okay, but so just so I understand, in again, biology naivete, right? This phosphorylation stuff, it's like snipping type. It's like single nuclear. I mean, it's sort of single peptide things. It's not like over a range of over a.
That's right. Yeah, it's individual residues that would be phosphorylated. Just typically only one.
Okay.
Some enzymes you can it's MAPK. You can phosphorylate it up to 3 times. I forget what the MAP stands for.
Okay. Is there a notation for a phosphorylated protein? Is there any standard notation, like in the sort of the standard kind of stringy bioinformatics world?
John, I defer to you on that.
I don't believe so, actually. I think that they resort to annotations as well.
Okay. What other kinds of annotations are there? I mean, there are obviously annotations that represent the meaning of some sequence, right? Like how do you say, or do you carry along, hello, this is the binding site on this protein? Does that get carried in the data structure?
Yeah, and we have one right here, kind of on the second line, the TF kind of binding site.
I see. How big is that? When you're talking about these types, how big is that? I see. So there's a gene there. Oh boy. I do not like this. Strand plus. Oh boy. Okay, so there's a kind of a calculus of annotations here, which, I mean, so for example, let's say that you had type gene strand plus blah blah blah. Then you say complement. You take biosequence complement. What does it do? Does it change that annotation? What does it do?
I think in the case of a reverse complement, that's one of the few cases where you can preserve a lot of these things. You've kind of gone over to maybe kind of like the negative strand. Of course, but these sites then are no longer meaningful because you're no longer, what's on the complement strand is no longer coding for this Eden gene. So I think most of the operations would end up
stripping.
Complement would throw it away. In the case of something like where we say translate, that's kind of the advantage of this notation, is that then we translate this BioSequence modify splice by feature, and we can use the coding regions to actually, splice out kind of one or the other proteins that actually come from this.
So you're saying that in the translate, you would actually be using these annotations to decide how to do the translation.
Yeah, we could. Yeah, that's great.
Well, so in principle with translate, then you probably need to give two cases, right? Well, what is it? Okay. How do you drop the annotations? Let's say I have a biosequence and I just don't want the annotations. What do I do? I mean, presumably there's an accessor for BioSequence that drops the annotations.
Right. I mean, because
that's going to be a killer for people. And maybe not. I mean, maybe they want to carry the stuff along.
It would be just one of the modify strings.
Yeah.
I see. So you'd have to do that. All right, but otherwise,
I don't see it quite as annotation. I see it more like in molecule the bonds.
I see.
It's not some random have it or don't have it.
Some of it is, but some of it is.
Some of it is, yes, correct.
It's this gene is called blah, blah, blah.
Yeah, maybe we should separate them potentially.
You mean things that have structural content versus, I mean, so this is an exon. What is CDS? What is CDS?
That's the coding regions. So these are the things that actually, once you kind of finally get down to the base level, these are the regions that are grabbed to make the protein.
And what's the difference between the introns? Is that, I thought, again, biology naivete, right? I thought there were introns and exons, and that, what's the difference? Okay, biology moment. Can somebody explain this to me? How does this work? When you have, I thought you had coding. I thought the exons were the coding region, and the introns were the non-coding region. Am I completely wrong? How does this work? Somebody help me out here.
I do not know.
I think it's yet there's kind of yet another step. These are what kind of will leave in terms of the kind of there being messenger RNA. So that's the stuff that'll actually get out there and travel to the ribosome. But what actually ends up getting finally processed ends up being these coding sequences.
Which are subsequences there. So gene splicing structure here.
That's right.
This is a rather simple gene that I've picked here. Okay. And intron there, which is snipped out, right? The exon, which is a coding region, is it not?
It also includes things like the initiating sequence to the ribosome. Fine. So
yeah, I get it. Okay. So you're saying CDS is a subset of the exons. That is the actual transcribed sequence without stop codons and all kinds of other junk like that.
You got
it. Yeah. Okay. So this is in fact an overcounting. So there's an incompatibility. I mean, if I said I have an exon and it's here and the CDS was not within the exon, I'd have to be lying. Is that correct?
I believe that's right. Yeah, that's right.
Okay. And is it deterministic? Given the exon, is it deterministic what the coding region is? Or is that still, because clearly,
No, even given, in this case, there's kind of the same mRNA transfers both the protein 3 and protein 4. So there are cases where even there's still room for variation.
By the way, I'm curious, Sandra on the live stream is mentioning the SEPT1 gene disaster and Excel. And I am just curious whether that just sort of missed by a few months you know, the work that's now getting announced with us and Microsoft and Excel. It's kind of a sad thing if that just missed by a few months being perfect, of not having to have that issue. Interesting. Michael probably knows, but he might not.
Yes, I'm working on it.
Okay. Okay. Well, so what else do we need to discuss about this? I mean, so this, I find this strand plus thing absolutely horrifying. If we're going to say this, it should be PLUS, not a quotes plus sign, I think. I mean, we might have some shortened notation.
Agreed, yeah.
Yeah.
But anyway, this was post 12.2, which just want to make sure that we have structurally a way forward for more complicated things that we want to add to the things that we want to add for 12.2.
Right, but so what you're saying is, I'm just utterly confused by this. I mean, this mRNA is saying how to peel off. No, I'm just monumentally confused here. I mean, I thought, but you see, this is one feature of biology that you know, when I learned it, you know, 50 years ago in school or something, you know, there were all these, you know, organelles of unknown function and stuff like that, and now, you know, or like there were red blood cells and white blood cells, right? And now there are, you know, CD8 positive, you know, T cell something or others. It seems like it's a self-similar thing that every time you think you know how biology works, it's got some other level of complexity. So I don't know I just have no idea what the difference between the mRNA, the exon, the CDS, and so on are. And do they really occur together? But I think maybe we don't have the right group to answer that here.
Maybe when we review the ontology of these for when this entity domain
I mean,
goes
the main point here is that what you're expressing here is both pure annotation. Like if we have a graph and we're labeling, you know, this edge is going to be labeled with, you know, I don't know, predator of or something like this, right? It's just a label. The actual structure of the graph says you're joining, you know, fox to hare or something, right? But and that's what's in the graph. But then there's a label that says something, and there's a quite different thing. Well, I mean, this is so complicated because most of our graph operations are label independent, so to speak. They just do what they do to the graph. And then our calculus of annotations theory is basically saying which annotations get carried along when what happens. Am I making sense? Like when we do a graph union, we can carry along some annotations but not others.
Right.
So the question is, here you're saying, and I'm confusing myself, but I mean, in a graph, we have things like weights of edges, weights of vertices, and so on. And some operations take account of those and others do not. And I suppose that's the analogy to what you're doing here with, you know, this piece is part of the coding sequence. And some operations care about that and others do not.
Yes, that's right.
Dan on our live stream is saying exons can be non-coding from a pre-mRNA before splicing, or the post-splicing RNA does not have an open reading frame. CDS typically spans multiple exons. Okay, thank you. I understand that. This is in the, yeah. Okay, all right. So I mean, these all have slightly different meanings is the basic point. But what we're saying design-wise is it's like a graph where what we do right now is to have annotations that represent things like vertex weights. But there is a base level of the graph that you can just, you know, manipulate as a graph without knowing about those weights. And I suppose that here we're doing essentially exactly the same thing. Michael, do you agree with that analysis? I mean, that this is similar.
I think so. Yeah.
And what's the analogy in the chemistry system to this? I mean, in other words, if I wanted to annotate a molecule saying, this part of the molecule is very important, or this part of the molecule has some special feature, do we have a way to annotate inside molecule like
That's
that?
a active area under discussion in the chemistry group.
Okay.
Yeah,
James,
Is that
what you
related
say?
to the stereochemistry business?
The stereochemistry would fall into that category where it might be destroyed depending on the modification you make.
I see. And what else?
Right, but I
other
mean,
than
just
stereochemistry?
general, like
Yeah.
this is my special carbon or something. We have the user would just keep track of that separately.
Right.
Yeah.
Although maybe we should allow them to do that. I mean, by the time, the stereochemistry has direct consequences for things like, rendering of the molecule and things. But what other annotations are there? I mean, I have to believe. Again, I'm stretching my knowledge of chemistry, but aren't there these weird? What are they? See, this is so embarrassing. I know this subject so poorly. I mean, these resonant bond thingies and things, these weird kinds of bonds that happen and so on that are not captured by your standard bond representation. Am I right, or am I talking?
That would be delocalized bonds, perhaps. If you,
yeah, that's one thing.
The closest we have are the aromatic that have their
which
own
is a very
special
specific.
type.
Right. So
Right.
the aromatic bonds are a very specific type of delocalized bond. But in general, is it not correct that in the quantum chemistry of these things, that you could have stuff like that happening? Is that true, or is that not or is it locked down enough? I mean, in other words, at some level, you're describing a very mushy system because you're describing this complicated quantum mechanical system that you're trying to describe in this sort of simplified symbolic form. And I guess I'm asking, are there other things beyond stereochemistry that have some structural consequence that are, an attempt to describe better this quantum mechanical mush?
Right. I mean, the different levels, because I mean, at the end of the day, I mean, or at the bottom of the level, like with quantum mechanics, it is all just a big bag of nuclei with the electrons that follow whatever wave function they
Right.
have, and we put various levels of structure on that to help us understand it, right? So we've got these covalent bonds. And we were talking in the group about putting different types of bonds than the traditional ones, like hydrogen bonds or just...
Yeah, what on earth are we doing with hydrogen bonds?
Nothing at the moment.
Okay.
Which, if you give us a structure that that has a hydrogen acceptor near a hydrogen, then possibly it would show up in the force field energy that you compute, but maybe perhaps not.
Yeah, but I mean, representing an actual hydrogen bonded thing. I mean, you don't usually see. I mean, don't they usually have these things with little dotted lines and so on representing? Maybe I don't know what I'm talking about, but
they typically do with a dotted line like that, but we don't have a structural representation in molecule right now for that. We're talking about it along with other types of coordination, for example, between metal atoms and other atoms that have electron pairs like oxygens and nitrogens that could coordinate with it. But
so
we're just talking at this point.
Right. But if I'm going to be really difficult here, right? Imagine water, for example, right? Which we know has little clusters of molecules in liquid phase forming. At what point do we give up? So in other words, it is not the case that water is really H2O. It's really got some little, clusters of, I don't know, with some probability, it's got some cluster of 10 molecules or something.
This goes back to discussion we had in the very beginning. What do we mean by molecule? And I still stand more or less, this is one separated in an infinite universe. This is not a bulk material.
And we're definitely interested in making a data structure to represent crystals. But we think that that it should be as separate than the molecule.
By the way, this person, Claudio, is just working on some function repository stuff for crystals. I assume you've seen that.
Like NaCl, it can be under, with a lot of trouble, you can make the single free-floating NaCl molecule.
Right. Sorry, just confirm. Claudio, who's working with.
Yes, Bob, you worked.
Yes, Claudia was
yeah.
one of my students this summer. Yeah.
Yeah,
Okay,
yeah.
fine.
And we're
Okay.
definitely
Okay.
looking at that
Okay,
as
fine.
a place
Right.
to
I mean, he's
start.
going to put a bunch of stuff in the function repository as a kind of get a starting point for the crystallography stuff. I mean, it is not the end point, but it is a starting point, and it will allow people to do, basic visualization of crystal structures and so on in a nice, clean way.
Yeah, absolutely.
So,
I mean, so annotating atoms within a molecule, right? One way that has traditionally been done in software throughout the ages, I guess, for the past few decades, right, is isotope tagging them, right? You just and it's kind of a hack, but it works across different software structures, right? When you want to watch that carbon through a process.
No, you said it's carbon 13 or something.
Right.
That's horrifying.
It's portable across different software.
How do you represent? Does Smiles have a way to represent isotopes?
Yeah.
How do you do it?
So you use a hard bracket and you put the integer before the atomic symbol. So you
horrifying, beyond belief. You see, these are the kinds of hacks that eventually blow up in everybody's face. That's how you end up with spacecraft for the wrong. With the fuel measured in the wrong units and so on. Let's try to avoid that. No, but okay. So what you're saying is there is. But by the way, we have isotopes, right? We can deal with an atom that is a different isotope. Yes.
Absolutely.
But okay, so one of the questions is when you annotate a molecule, there is sort of point annotation of, for stereochemistry, obviously you're annotating a group of atoms to say, what is its, left-handedness, right-handedness, whatever else. So I guess my question would be, in general, you are annotating, and the same thing is coming up for these biosequences. You're annotating some kind of subset of the objects that are in the structure, some sequence of peptides, some collection of nearby atoms, etc. Usually, I suspect you're annotating nearby things in the structure, although that might not always be the case because you might have some folding thingy where there's some weird hydrogen bond that goes across two things that are that appear to be in different places in the structure. Is that correct, guys?
That happens in proteins all the time.
Right, but so my question is, what we're going to need in the end is annotations that are essentially a subset of the underlying objects. I mean, this feels very much like what we're doing in meshes, for example, where we have these underlying things, and then we're putting a sort of superstructure on top of that says you've got these underlying points, you've got these underlying polygons, whatever else. Now this is how you are coordinating them together for purposes of this annotation.
And those go in your mesh after the list of coordinates, right? So you've got
that's correct.
Your list of coordinates, your list of points, and then relationships among those points, and those are defined relationships, each with their own head, right? The polygon, line, those types of those elements.
I think there are other relationships that you can give too, but yes, right.
And so having those defined heads, that's how I view the stereo, right? I mean, it's a relationship between a group of atoms. But I mean, we've got the ability to go further with just plain annotation rules, right? So if we want, we can apply. So I don't know how related this is, but I mean, you could imagine have put all that stuff into an annotation rules option.
As in the graph, the annotation rules that we're using for graphs and meshes and so on. So
right, and I am definitely, putting those, trying to integrate those with molecules.
Okay, so what you're saying is a different plan, right, is to use the annotation structures of graph. I mean, one plan is what we do with meshes, where it's like you have the objects and then you give their relationships. Okay. Another plan is it's like graph where you have, well, in graph you have the same thing actually. The first argument is the nodes, the second argument is the edges. But and then you have annotations in addition to that. Right?
Right. And in the graph structure, if you wanted to put some type of, I keep thinking of them as hyperedges. I mean, this relationship between multiple vertices, more than two vertices, there would be no place in the graph structure. And you could imagine shoehorning them into the annotation rules.
Well, are you telling me that what you need is hypergraphs? Because we're going to have more hypergraph stuff. I mean, we've got, for the physics project, we've got really pretty good, we've got a lot of high-powered stuff for dealing with directed hypergraphs, which is actually exactly what you want for stereochemistry, I think. In other words, a hypergraph, often people think of hypergraphs as undirected hypergraphs, where you just have buckets of nodes, associated together at a hyperedge. But in the physics project, we have directed hyperedges, which is, I think, what you need for stereochemistry. Am I right? Am I wrong?
I think so. It's an ordered set of atoms.
That's what
and
we
if you
have.
change
And
the
a
order,
type
you change
of-
the
Yeah,
notation.
exactly.
Yeah.
Right.
That's what we have.
And so for us, I mean, I would give it a head like stereo group or something. I mean, so we've got multiple types of stereo that I would want to describe in this. And I really hope that I'm not derailing the BioSequence meeting with talking about the stereo stuff.
No, I think it's relevant because, I mean, basically what we've got, look, what we're trying to check here is that we're not cutting ourselves off for the design. And we're trying to check that there are basically two models for annotation. One is annotation rules. The other is the mesh-like way of doing it. Okay. I tend to think that, oh boy, I mean, there's arguments for both of them because, and maybe we have both of them, and maybe we have certain things in that are, it's complicated. It's complicated.
I mean, so with my first use case for annotation rules in molecule is, I mean, you want to specify what the tooltip on an atom or a bond is. You want to specify all the other wrappers that can be applied in an input form. They get put.
Why can't you just write tooltip when you put around an atom in?
Well, so that's the way that a user would enter it, but then in canonicalizing it, it gets put into the annotation rules.
Fine. I see. But if you want a tooltip, a cluster of atoms, can you do that or not? Like in a BioSequence, you might want to tooltip some region in the sequence. By the way, when do we get viewers for the? I mean, like the picture that's on the right in Wolfram Alpha. When will we get something like this in the language? Because this thing here is basically, presumably, I could have a sequence here, and like these exons and things like that. This is exactly what I'm, I should be able to display these kinds of things, and that's what all of these, last 15 years or something, or maybe it's more than that. I'm losing track of time. These various hierarchical gene viewer type things provide.
Yeah, that's right. That'll come right along with the representation.
Okay, fine.
We still work on the representation, so when we got that out, we can do that.
Right. Question from our live stream about, do we have mass spectrometry and infrared spectroscopy data? We actually have a project. There was a project. There's a project underway for molecular spectroscopy stuff by an outside person. Maybe Bob remembers that. I'm not sure what. And in terms of mass spectrometry, isn't that just computing, counts of numbers of atoms and things? Or am I confused?
No, so I mean, it seems like you really ought to be able to make compute the mass spec from a given molecule or whatnot. But I don't.
Well, there are two aspects to that. One is the fragmentation of the molecule, and then for a given molecular ion, based on the natural abundance of the different isotopes, the peak
Right.
for that is actually a multiplet of certain intensities, and those intensities are very easily computed with certain assumptions about the natural abundance of,
Yeah,
of
like
the,
which mine did you mine that tantalum from?
well, yeah, I mean, even down to that. In fact, that's how they determine origin of different samples.
Right. Right. Okay.
And for dating as well, oxygen
Right.
18-16 ratios and so on.
Or famously carbon-14.
And carbon, well, yeah, well, that's trace. I don't know if you think you'll pick that up with mass spec.
I see.
Let's see, they mentioned infrared. At the moment, we're limited to, importing data from computational. So you compute the spectrum and you import the frequencies.
Although you guys are, when are you going to have electronic structure stuff? You were working on that, weren't you?
Right. So I had found a library that allowed computing it and wrote it. So it'd take a lot of time.
More and more of the electronic structure packages are starting to have libraries that you can plug into them so that they can be part of a bigger outside collection of software. So
time, as in to compute electronic structure for any given molecule, you'll be spending 10 hours of CPU time, or what?
No, I just mean we need a developer to spend. So I've written a lot of tools to automate the process of writing these library link packlets. And if I had somebody to work on that.
Yeah, okay. Should ask Sushma. I think she's got some relevant people now. You should make that. You should ask her.
Okay? I'm making a note.
Okay. Anything else we should make sure to cover in this meeting?
In terms of the core 12.2 functionality, we're largely good to go.
I think so. I think I'm
great
good with this.
Okay, then we will concentrate on the documentation and implementing more of the string functions.
Sounds good. Looking great. I look forward to seeing this. I need to run it on my own genome. I need to, presumably I can, with this, a standard workflow, right? I've got all the, I can pull up my mitochondrion or something. That would be a simple piece. And then I would just turn that into a biosequence. So presumably I should take my genome. Is that going to work? It's an in-core. I can read in the chromosomes pretty easily, right? And then what I should then get, I've got a FASTA file. So I would just say, by the way, will the FASTA import have a biosequence element? So I can import the FASTA file into a biosequence?
That's on the list.
But otherwise, I just say biosequence of DNA, import FASTA file, right? Am I correct?
You might have to grab out just the sequence part of the FASTA file.
No. What we do what was I going to say? Actually, this is amusing. I actually have got my whole sequence done twice now at about a 10-year interval, but quite coincidentally. And I've been meaning to compare the two, and I wonder what I'm going to find.
Yeah.
I don't think I don't expect retroviruses to have attacked me in the intervening period. I suspect more like the changes in sequencing technology. But anyway, so no, what you get from FASTA import is just a straight DNA sequence. That's the default element for FASTA import. Now I don't know which. There's often some strand confusion, right? So if I just say biosequence of DNA, and then some sequence, what is the strandiness? What is assumed there? Do you understand my question? Is that the plus strand?
By default, there's no strand assumed. It's indeterminate.
What do you mean? I see. So, but if I take my mitochondrion, right, and I just import it, I've got, I got the FASTA file, the
and right, and then you want to map it against the reference. There's a function that's not going to make this release called locate BioSequence, where it figures out where it is on the genome and assigns the strand and the positions and all that good stuff.
But we have already genome lookup, right?
Right. So you can do that too. Yeah.
I mean, if I just type in some random, if I type in, I mean, we've had this for like more than a decade now. If I just type in some random sequence here, the default will be, so that, by the way, presumably can be replaced by biosequences. Is that true? Should be replaced by biosequences.
No.
You have no chromosome at the moment.
Because this is not a sequence, this is the position on some higher structure.
Yes.
But we're going to need that.
Yes, but probably I would say more through entity-related things.
Really?
Isn't not kind of an our world chromosome 1 and the most natural view an entity that has certain properties?
Oh yeah, for sure. That's right. But this structure, this data structure, if I say, go turn that thing into an actual sequence there.
Oh yeah, yeah. Yeah. So these could give back embedded biosequences, which then you say, just give me the sequence that's found in this
I mean,
structure.
and for example, we know what build number that chromosome was, and that obviously that would be in the entity information.
Exactly.
But you're saying, I mean, in general, I would want to take some sequence and I would want to annotate it in some way, because I want to know what, I mean, like I take my mitochondrion and I want to find, haplogroups or whatever it is. What's the workflow for doing that here? So I've got my mitochondrion and it's a biosequence. Somehow the FASTA file, presumably, and the level of the FASTA file, it knows whether it's a plus strand or not. Correct? And right now we are getting rid of that.
Not necessarily.
Okay, fine. But if it does, we should preserve that when we get the biosequence out, because right now what we're doing is, if I just take a random FASTA file, I'm if I were just to pull in my genome, which is stored as FASTA files, I literally drag it into this notebook, it will come out as the default element. The default element is the is that sequence, unknown whether it's the plus strand or not, presumably is the plus strand. But if we had BioSequence, then perhaps that default should change to being the full BioSequence, which says which strand it is and so on, right? And the FASTA file presumably says that it's DNA, not whatever else. And then what is concerning me slightly is the obvious thing I'm going to want to do is compare that sequence to the reference sequence and find SNPs and things. So what is our imagined workflow for that? Because finding SNPs is very similar to what I just did up there with genome lookup, which is I want to say, it's in the end, a disembodied SNP is a relative to this, reference biosequence. A reference relative to a reference biosequence, so to speak. Am I making sense? I mean, this is an example of that.
Yep.
This is a generalized SNP, what we have here on the screen. How do we imagine we're going to do this?
Yeah, so there's a function that's not going to make it called locate biosequence alignments, which takes kind of the biosequence that's given in and finds an alignment with the reference sequence. And from there, we can also specify, once we have the alignment, we can say, okay, what SNPs occur along this alignment, we have.
I get it, but what we don't have is a representation of, you know, RS blah 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 SNP, right? That, you know, that is something which is relative to the reference sequence.
Yeah. That you get back a kind of the list of, you know, of structures that say, here's what the SNP is, here's where it is on the biosequence you provided, here's where it is on the reference sequence, here's what the flanking sequences are.
Yeah.
Yeah.
Yeah, something like that. I mean, but I think there's a missing structure here, which is the thing we're seeing on the screen, which is something we don't have in many other places, which is you've got a string and now you're saying it's characters 7 through 11 of the string.
Right.
You know, we don't usually have a structure that means that. We don't need that structure. You either take out those characters or you just have the
There's a post 12.2 structure, which is unfortunately broken right now, called embedded biosequence for this purpose. Where you say we have some larger reference feature or some larger entity, and we're just talking about where the coordinates are, and from it you can get back, okay, what sequence are you referring to? What's its flanking sequences? What strand is it on? All this kind of good stuff.
Right. Okay. Okay, sounds good. Okay, anything else we need to cover? Nope. All right. Well, thanks everybody.
Thanks everybody.
Thanks everyone.
Thanks Emerald.
Thanks Stephen. Thanks Emerald.
Yep, and thanks